Hi, everybody. Welcome back to the last and final chapter that we're going to be doing this semester. This chapter is on the subject of light and matter. This chapter is not in your textbook, so all the learning you'll get and the reading you want to do will be available only from through these slides. So you'll find them on Blackboard and you can use them from there to study from. Let's start off with the first slide from this. And as you know, we always usually start out every chapter with a photograph. And here's a photograph. I don't know if it looks familiar to you, but it's a photograph of a nebula. This is an area in space, right, where gas and dust collects. And in fact, this is an area of a nebula where stars are being born. And you can see in this bright area right here, this is an area that stars are being born in. Well, what does this have to do with light and matter? But what I wanted to note for you to notice about this is the colors. If you see the colors here, you'll see some yellows, you'll see some reds, you see some blues, some purples, some whites, and that's giving us some information through light. We're seeing colors of light. And does anybody know what those colors represent? Well, those colors represent temperature. Okay? Something that's hot could be very hot. In fact, could be either blue or white hot. Those are the hottest. And the coolest, maybe you'd say, are the red. The red objects are the coolest. The blue are the hottest. Okay, that's what color of light represents to us. It represents something about temperature when we look at it in the stars and in space. And just like, so one of the things I'd like you to notice too is that most of you probably at home have gas ovens and gas stoves. And sometimes if you ever look at the flame coming out of a gas stove or stovetop, you'll see the flame goes from red to yellow to maybe a bluish. Well, the point where the flame is blue is the hottest part of the flame. The part that's yellow is not as hot, and the red is the least hot of all of them. So if you want to put a pot on the stove and you want to heat it up really quickly, make sure that the blue portion of the flame touches your pot, and because that is the hottest. So what this picture wants to explain to you is that light, okay, light color represents temperature. So I want to start the discussion now of light and matter, and it's going to start off with a discussion of light and as an electromagnetic wave. We're going to be using that term a lot in this chapter. Some of the things we're going to be talking about is what kind of information we get from the skies. When we talk about waves, waves in what kind of material? What are we talking about? And we'll talk about those. We'll talk about the electromagnetic spectrum. We'll talk about thermal radiation, spectroscopy, spectral lines, Doppler effect. All these things are related to properties of electromagnetic waves. So these are the things that we're going to do. This chapter is not as long as some of the other chapters are, so we should go through it in about 3 sessions. We should probably be able to complete this chapter. Let's start off the first slide, and I want you to understand what we mean by electromagnetic radiation. Okay, electromagnetic radiation is, and I'll read it right from the slide there, is the transmission of energy through space without any physical connection. Okay, that's how we can get information from space without a physical connection, and it's using electric and magnetic fields. That's why it's called electromagnetic radiation. And an example of electromagnetic radiation is light. light is electromagnetic radiation, and also heat is electromagnetic radiation. The heat that you feel from a campfire or for a flame, the way that heat gets transmitted to you is through what's called electromagnetic radiation. And you can see here I have a picture of the great galaxy in Andromeda. Okay, the light reaches us, okay, via electromagnetic radiation traveling through space. At what speed? Well, at the speed of light. So electromagnetic radiation is the transmission of energy. Okay, and when we're talking about light is electromagnetic radiation, it's light being transmitted to us. We know that there's no physical wire connecting us and the Andromeda galaxy. We see it because these electric and magnetic fields are traveling through space, coming to our eyes, and our eyes are sensitive to this electromagnetic radiation. And don't forget also that heat is another type of electromagnetic radiation. Okay? So, we've introduced this concept now of electromagnetic radiation. Okay? It's energy traveling through something via electric and magnetic fields. What do we mean by all of this? Okay? Let's take a look at first these. We talk about electromagnetic radiation. Electromagnetic radiation is a wave. What is a wave? Okay, a wave is energy transmitted, okay, without material being transmitted. Okay, but here's a wave, for example. Look at this. We call this a sinusoid, this little wave. And if you look here, here's the wave, okay, and it's characterized by a certain wavelength. The wavelength is the size of the wave from one position of the wave to the next corresponding position on the wave. So the wavelength is, we call the wavelength of a wave from one peak to the next peak. That's the distance, whatever it is, in meters or whatever, we call that the wavelength. The wavelength could also be called, we can measure the distance from the bottom of the wave, what we call the trough, to the next trough. Okay, that's also the wavelength. Or the wavelength can be from any point on a wave to any other similar point on that wave, to the exact same point. Not similar, but exact same. For example, if I have this point X right here on the downslope, I can measure the wavelength to the next point where it just goes to the downslope right here. So the distance between this wave, this position, and this position, that's also a wavelength. So the wavelength is a characteristic dimension of the wave. It could be in meters, it could be in microns, it could be in billionths of a meter. It's all different size waves we're going to have. So one characteristic of a wave is one, its wavelength. The next is its amplitude. That is, how high does the wave go from a position where it's at rest? For example, if I had a rope tied to a little hook on the wall and I pull the rope straight, this is the dotted line represents the rope I pulled straight. As I move it up and down, I create a wave. Here's the wave I'm creating by shaking this rope up and down. This is its rest position, okay? And this is its position in the disturbance. When I disturb it by moving it up and down, I'll get this. And the height at which it moved from its rest position, we call its amplitude. So the amplitude of a wave is the amount of the disturbance, the height of the wave, the amount of the disturbance. So this dotted line represents, as we say here, its undisturbed state, okay? And when it's disturbed, when we put the disturbance in, it reaches an amplitude. It reaches a height that we call its amplitude. So this is a wave here, the way I show it in this drawing is that the wave is actually vibrating. It's just being disturbed up and down, and it's moving in this direction to the right of the wave. We say it's moving this way. So we've learned a couple of things about waves. We learned about its wavelength. which is a measurement of the wave, how big it is in terms of meters, how many meters it is from this position to this position. Or it doesn't have to be meters, it could be centimeters, it could be micrometers, it could be all sorts of things. So, as I said, the wave is moving to the right, as we can see in this, and we learned about wavelength and we learned about amplitude. Okay, wavelength is the measurement of the size of the wave from one point on the wave to the same corresponding point in the next wave, wherever it repeats. As you can see here, we start from this point right here to this next point where the wave repeats. That we call the wavelength. Next is, let's talk about what is the frequency of a wave. Okay, the frequency of a wave, and I can show it to you a little easier by looking at the diagram we have right here of these two waves right here. If just naturally, if I ask you what is the frequency of a wave, okay, I'll say to you, well, which you think of with these two waves, which one has the higher frequency and which one has the lower frequency? And hopefully you'd say that, well, if I look at this one probably has a low frequency, and this one on the bottom here has a higher frequency. In fact, it even says it, low frequency and high frequency here. The frequency of a wave is the number of wave crests, or the number of the wiggles of the wave that pass a point each second. The number of wiggles per second. Okay, and you can see here, in the case of this wave right here, if I go from this point right here, I draw the line straight up and down, from this point to this point, okay, it looks like the wave has moved through exactly one wavelength, because I go from the peak of this wave to the peak of the next wave. That's one wavelength. So we say that if I'm moving between this point to this point right here, the frequency of this wave is one wave per second. If the distance between this timing between this point and this point is 1 second, and one wavelength went by in that 1 second, we say that that wave has a frequency of one wavelength, or one cycle per second. A cycle is a wavelength, the same thing. So we say that the top wave has a frequency of one cycle per second. And cycle per second have a designation in science, and we call that, one cycle per second is called 1 hertz. And the hertz is abbreviated Hz. Sometimes you can see on a radio dial, when you're dialing in a radio station, you're dialing in, it's actually an electromagnetic wave, and you're dialing the radio to its frequency. And sometimes you'll see the frequency displayed in MHz is written on there, or KHz. It means millions of hertz, or kilohertz, thousands of hertz. Hertz was the name of an English physicist who first started explaining about waves and measuring waves, and they gave the honor of him of the name of a cycle per second called a hertz. I remember one of my instructors used to hate terms in science that were named after people, because it really doesn't give you any idea of what really they're talking about. It's really better to call it a cycle per second. So going forward, I'll try to say cycles per second instead of hertz, but I may slip once in a while. But every time I say a hertz, I mean a cycle per second. So as I told you before, this top wave right here has a frequency of one wavelength, or one cycle in 1 second, because when the wave travels from this position to this position, that timing is 1 second. Let's look at the next wave, the one on the bottom here, the one that we say has a higher frequency. Let's see how many wiggles, or how many cycles or wavelengths go in 1 second, travel from this point to this point in 1 second. Well, if we follow this wave, here's one wave, here's two wavelengths, and now three wavelengths. So the bottom wave has a frequency of 1, 2, 3 cycles per second. So we say that this wave, the one on the bottom, has a frequency of 3 cycles per second, where this wave has a frequency of only 1 cycle per second. So this wave is lower frequency than this wave. We can see that in the time frame of this window, which I told you the window is 1 second, only one wave goes through here, whereas you get 3 wiggles here. So this is a higher frequency wave than this one. And that's what we mean by frequency. How many wiggles go by per second? The more that go by per second, the higher the frequency. And the unit that we use to measure frequency is in seconds. How many cycles go by in 1 second? And let me give you an example, another example of cycles per second or waves per second that I hope you can understand to try to give you a feeling for frequency a little better. If I tell you that you're standing on the shore of the beach and one wave crashes at your feet, if you're standing right at the edge of the shore, every 1 second, a new wave comes crashing right at your feet. So that's essentially the top of the crest of the wave. So therefore we say the wavelength of those water waves that are hitting your feet are 1 cycle per second or 1 wave per second, 1 hertz. Let's say now you're standing there and 3 of these waves, like the wave below, 3 of those hit you per second. That's awful fast, but let's assume that's happening. 3 of them hit you. Then you'll say that the wavelength is 3 per second. Well, let me think about this one. What if you're standing on the beach and one wave hits your feet, that's the beginning. The next one doesn't hit your feet for 2 seconds. So it takes 2 seconds for a complete wave to hit your feet. What is the frequency of a wave that takes 2 seconds to reach you? Think about that for a minute. If it takes 2 seconds to reach you, then half of the wave can come to you in 1 second, and the next half of the wave comes to you in the second second. So therefore, we say that the frequency is not 2 waves per second, because it's not. It's exactly 1/2 a wave per second. Okay, so if you're standing on the shore and a wave hits your feet every 2 seconds, we say it has a frequency of 1/2 cycle per second, because in 1 second, only half of the wave travels toward you. Let's say in another case, you're standing on the wave and it's standing on the shore, and it takes 5 seconds for a wave to hit your feet. Every 5 seconds, a wave crashes on shore. Its wavelength is then 1/5 of a cycle per second, because it takes 5 seconds for the wave to reach your feet. Okay, the wave is not 5 cycles per second, because 5 cycles per second means 5 waves travel in 1 second, but the wave is a lot slower. It actually takes 5 whole seconds for the 1 wave to come to you. So its frequency is 1/5 of a hertz, or 0.2 hertz. 1/5 is the same as 0.2. So learn something hopefully about the frequency of a wave. Let's look at now wavelength. There's the discussion of wavelength. The wavelength is the distance between successive crests or successive troughs of a wave. And the velocity of a wave is just like the velocity, just the velocity that we always talk about. Velocity is speed, and the speed at which the wave moves is called its velocity. And in general, the velocity of a wave is equal to its wavelength times its frequency. Okay? The wavelength is measured in meters per second, and its frequency is usually measured in cycles per second. So that's the velocity of the wave. Well, when we talk about waves, let's think about waves for a moment. Let's talk about a water wave. Okay? And if we have a pond, like we see right here, and a stone falls in the pond, and you'll see there's a stick floating on the water right there. As soon as the stone goes into the pond and causes these ripple waves, you'll see a wave looks like it's going to emanate. It's going to come from this little disturbance. And what do you think the stick is going to do as the wave goes by? The stick is actually just going to follow the position of the wave. A water wave that just moves up and down, that's all it does is move up and down, is called a transverse wave, hence the term a transverse wave. You can see right here, here are the ripples, and it's going to travel, and these ripples are going to travel towards the shore. And what's going to happen to the stick? Well, this little diagram represents that. Here's the disturbance before the stone hit the pond. And then after the stone hit the pond, these numbers represent different positions in the water. Let's say 1 is here, 2 is here, 3, 4, 5 as we go out. So you can see what's going to happen to the stick. The stick is just going to ride up and down on the water. The water is going to rise and fall. It's going to rise and fall. And the stick, all the stick is going to do is going to go up and down. Even though the wave is moving to the right, it's moving out, the wave is traveling towards the shore. The energy is traveling towards the shore. The stick only moves up and down to show you how this transverse wave behaves. A transverse wave is a wave that just travels up and down while the wave moves to the right or to the left. Okay, in this case, we'll say the waves are going to be moving in this direction. The stick doesn't move in that direction. The stick, all it does is going to go up and down while the wave moves in this direction. So, a transverse wave is a wave that moves up and down, but the wave travels in the opposite direction. It moves in a perpendicular direction. That's what transverse means. Transverse means perpendicular to. So while the wave vibrates in the up and down direction, the wave travels in the transverse direction. There's also another type of a wave called a longitudinal wave. Here's a longitudinal wave. A longitudinal wave is like a slinky wave. You ever seen a slinky? Here's a slinky. All right. And a longitudinal wave vibrates and travels in the same direction. Just here, you can see here, as I pull the slinky out, it's going to move back and forth. That's what we call a longitudinal wave. Okay? So I want you to understand the difference between a transverse wave, which is a wave that goes up and down, just moves up and down, but energy is traveling perpendicular or transverse to it, and a longitudinal wave which moves where energy moves in the same direction that the disturbance is moving. That's like a slinky kind of a wave. So those are the two types of waves, transverse and longitudinal. Let's also talk about, the reason I'm going over all of this is we're talking about electromagnetic waves. So we talked about waves like water waves. Okay, we understand that. And I want you to think about for a minute a magnetic wave. Magnetic waves are caused by magnetic fields, called these magnetic waves. And I had told you before, the Earth has a magnetic field. And here you can see in this diagram here, this is the field lines. These are the lines of force, the lines of magnetic force that are coming out of the Earth. The Earth has a magnetic field because of material in the center of the Earth is still molten. There's molten metal like iron and nickel in there, and that metal is moving. And when that moves, it creates a magnetic field. And that magnetic field, okay, has a direction where we have a north magnetic pole. So the field starts from the North Pole or starts in the South Pole. I guess maybe it starts in the South. I don't know where it starts from, but the arrows here show it going from south to north. So the field lines travel in this direction. So we say this is the axis of the magnetic field, and the magnetic field travels from south here to north. We know also if we put a compass needle in a magnetic field, the compass needle will line up with the directions of the lines of force of a magnetic field, and that's why the compass points north. So this is I'm showing you here that the Earth has a magnetic field and it has these imaginary lines of force coming out of it. You can see them a little more clearly here, and this is a bar magnet right here, just a little bar magnet. And there's a piece of paper on top of this bar magnet, and on top of that paper are sprinkled iron filings. If I were to take a piece of iron and just braid it down with a little file, and I take little pieces, or little pieces fall up, these little pieces, notice how they line up with the field lines. They actually show you the lines of magnetic field. Just like in the Earth is acting like a bar magnet, you can see right here. Here's actually a bar magnet. Okay, you can actually see the field lines. The lines of force are aligning the little iron particles, just like a compass needle points. So this is a magnetic field. A magnetic field is created by the Earth, is created by other types of objects, like all kinds of magnets. There are also electric fields. Okay? And this is a pretty important concept to understand, is that when we have electric charges exist in everything in the universe. Everything in the universe is made up of atoms, okay? And atoms have electrons that are moving around the nucleus, around the center of the atom. There's electrons. And these electrons carry a negative charge. Here's the electron, this little blue ball, if you will. I just drew it here. An electron has a negative charge. And the nucleus of an atom is made up of protons, and protons have a positive charge. Okay? These little red balls would represent positive charge. And try to remember that protons have a positive charge. P and P, proton positive. Electrons have a negative charge. Okay, and these charges, there's electric charges in an atom, in every material in the universe. There are moving electric charges. The electrons are moving around the nucleus the way a planet moves around its star or the sun. That's what we call an electric field. An electric field is produced just the way a magnetic field is produced. An electric field is produced by these charges, by the electrons and the protons in something carry electric fields. But one additional thing is that when these electric particles, when they move, the electric fields that move with them create magnetic fields. This is a property in physics that somebody by the name of James Clerk Maxwell told us that when you have a moving electric charge, it creates a magnetic field. And when you have a moving magnetic field, it also creates an opposite electric field. So moving electric charges cause magnetic fields, and moving magnetic charges create electric fields. So what I want you to see from this is that because everything in the universe is made up of atoms, and the little particles inside the atoms are always moving, the electric charges are always moving, These electric charges have electric fields, and when they move, they create magnetic fields. So electric and magnetic fields are traveling together. Every particle in nature, everything in nature has an electromagnetic field. Because atoms consist of moving electric charges, these moving electric charges cause magnetic fields, and as a result, electromagnetic radiation comes out of every atom in the universe. Every atom, the atoms that make up your computer, the atoms that make up your desk, that make up your body, they're all in motion and they're all giving off electromagnetic radiation or electromagnetic waves. Okay? Electromagnetic waves are given off by everything in the universe. Everything. Okay? And an electromagnetic wave is a transverse wave. I'm going to explain to you that it's a transverse wave. So somehow, because of these moving electric charges in atoms, okay, because charges are moving, it generates these electric and magnetic fields, and these magnetic and electric fields are intertwined in a position like this one. Let's look at the next slide. Electromagnetic waves oscillate in perpendicular directions. The electric field is shown here by, let's say, this little pink plane. This is the electric wave that's vibrating. And perpendicular to it is the magnetic field. And this is typically how electromagnetic waves are made up. Electromagnetic waves are made up of two perpendicular waves. One is the electric field is perpendicular to the magnetic field, and they're moving either up and down or side to side, but the energy is traveling in a different direction. As you can see here, here's the electric field moving just up and down, and here's the magnetic field moving side to side, but the wave is moving in this direction. And when we say when the direction of propagation, when the wave moves in this direction but vibrates in the other direction, that's called a transverse wave. And an electromagnetic wave is a transverse wave. And the important thing to remember is that in nature, because there are charges moving inside of atoms, every material, everything emits electromagnetic waves. Now, the question is, what is their wavelength, or what is their frequency? Wavelength and frequency are tied together. Okay? If you have a very long wavelength, that's a low frequency, right? If we have a very short wavelength, then we have a very high frequency. So frequency and wavelength are pretty much tied together, and you can almost use those terms interchangeably to describe a wave, almost interchangeably. So, important thing now is that we learned about electromagnetic waves. I gave you the example before. Light waves are electromagnetic waves. Heat waves are electromagnetic waves. There are a lot of other things that are electromagnetic waves we're going to learn about in just a moment. But electromagnetic waves are generated whenever an electric charge, like in an atom, is in motion. So when charges are in motion, they generate electric waves. They can be either magnetic charges that are moving or electric charges that are moving. When electric charges move, they create magnetic waves. They create a magnetic field, so you get an electromagnetic wave from that. Or when magnetic fields move, they also cause electric waves. And there again, so a moving electric or magnetic field creates an electromagnetic wave. And those waves are transverse, just like the one you see pictured here. I want you to think about this for a moment. What is the difference between electromagnetic waves and other kind of waves that we know? There are water waves, there are sound waves, okay? But we know that water waves and sound waves need a material in which to travel. Water, for example, we couldn't have water waves if there wasn't water as a medium. Okay, water waves travel through water. Well, what about sound waves? Does anybody know what sound waves travel in? Well, sound waves, they also need a medium to travel in. Water waves, sound waves, we call those mechanical waves. Those are mechanical waves. Mechanical waves mean that they need a medium to propagate in. Like water, air, we know that sound gets propagated in air. Okay, here's a little diagram right here just showing you. Sound waves are pressure waves. They're not electromagnetic waves. Okay, electromagnetic waves are created by charges in motion. In water waves, the only thing that's in motion is the water. Okay, the water is moving up and down. Yes, water is made of atoms and it has electromagnetic waves, yes. Sound waves, though, but we're talking about just the waves of water. And sound waves are just pressure waves. That is, the pressure in the air changes, and as the pressure changes, here you can see these pressure waves reach your ear and your eardrum vibrates. As your eardrum vibrates like a little drum, it's connected by little bones, it's connected to your brain, okay, to a nerve, and your brain interprets these mechanical waves as sound. So sound waves, okay, are pressure waves in air. If you were to suddenly release all the air, let's say from the room that you're in right now, you would not be able to hear any type of sound. Because if there is nothing to propagate the wave, like there's no air, you would not hear the sound. And in space, there is no air. There is nothing to transmit waves. So sound waves cannot travel in space. Okay? If, despite what you see in all these Hollywood special effect movies of things blowing up and you hear the explosions and everything, that's only a special effect. That can't happen because there is no medium to transmit the sound in outer space. And therefore there is no sound. I don't know if a lot of you have seen the movie a couple of years ago. There was a movie with George Clooney and Sandra Bullock called Gravity, where their astronauts were above the Earth and they were in space, and they were in the space station, and meteors were colliding with the space station, and they couldn't hear them. They could see all the damage, but they couldn't hear them because there is no air in space, no medium to conduct sound. Okay, and that's why there's no sound in outer space. That's why I've shown you here. You can have this little, that astronaut. So let me talk about these electromagnetic waves. Electromagnetic waves travel in space, and they do not need them. What's different about electromagnetic waves is they do not need a medium to travel in. Electromagnetic waves can travel through a vacuum. That's the difference between a mechanical wave and an electromagnetic wave. Electromagnetic waves travel through space. They can travel through nothing. When we see the Andromeda galaxy, we can see the electromagnetic light, the light from those electromagnetic waves reaching us from 2.5 million light years away. It's traveling through the emptiness of space. So that's the difference between an electromagnetic wave and a mechanical wave. Electromagnetic waves travel in a vacuum. They don't need a material to travel in, whereas pressure and mechanical waves do. And in fact, when electromagnetic waves travel in a vacuum, they travel at what speed? At the speed of light. They travel at the speed of light, 300,000 kilometers per second, or roughly 186,000 miles per second. That's the speed that electromagnetic waves travel in a vacuum, in nothingness. Okay? But if an electromagnetic wave has to travel through something like air or water or glass, it slows down. Okay? It travels its fastest, that 186,000 miles per second, only in a vacuum. It actually slows down when it goes through air, water, or glass. And when it slows down, the light bends. Light bends. Here's an example. We call it refraction. Light bends when it slows down. So you can see right here. Here's a pencil sitting in a beaker of water. And it looks like the pencil is bent. And that pencil is bent only, it looks like it's bent only because the light that's coming to us from the water, the light travels a little slower than it does through the glass. So the light is actually bent, and you can see that the pencil looks bent. So when electromagnetic waves slow down, they change direction, okay? They don't travel in a straight line anymore. They get bent, and that bending is called refraction. Okay, and that's refraction. Here's an example of refraction. Example again is to look at this pencil in a glass of water. Try it, if you will, with a little spoon in a glass of water, and you can see that effect. Also, refraction, you're going to see, is responsible for bending light. And you can see when we pass light through this device here called a prism, when we pass white light through it, we're going to see that when white light goes through, it spreads into a lot of different colors. Okay, this is what's happening when the white light travels through a prism. White light, like from the sun, is made up of many different colors or many different wavelengths of electromagnetic light. Notice that when light travels through this piece of glass, it's going to slow down. So it was going in this direction. Notice now it bends, okay, when it goes through the glass. And as it comes out of the glass again, the light bends again. But each one of the wavelengths, there's a lot of different wavelengths in white light. There's a lot of different colors, or each one color is a different wavelength. The red bends the most, and the violet or blue bends the least. Okay, so this is called refraction. Refraction is the result of light traveling through a material where it slows down and it bends, and different wavelengths bend by different amounts. That's what we call refraction. So what we want to remember about electromagnetic waves is they travel very fast. They travel at the speed of light only when they're in a vacuum. When they travel through air, water, or glass, they go slower. And when they go slower, they bend. If you remember the experiment you did in the lab, you had to shine a laser through a piece of glass, if you remember, and you had to put little pins in there and measure the angle at which the light bent. The light bent because of refraction. That was the example that you did in the lab. You actually measured how much light changes direction when it goes through something, when it has to go through something. Usually air, it doesn't slow light up very much at all, only a few percent. But when you go through a medium like water or glass, a more dense material, then light slows down more. It bends a little more. So when it goes from a vacuum of space into our atmosphere, into the air, it doesn't bend very much. But when it starts going through water or starts going through glass, then it bends more. It refracts more. So we understand something about the speed of electromagnetic waves, all right? They travel at the speed of light. Mechanical waves, as I told you, travel much, much slower. Mechanical waves, the speed of sound, for example, is only 1,100 feet per second. But sound and the water waves, they need a material to travel in. Okay? Sound waves do not travel in space because there's no material There's no air in space to give us this pressure wave. But electromagnetic waves do not need this. So what I want to do is now, we talked about electromagnetic waves, and I told you that everything in the universe gives off electromagnetic waves because the atoms are made of charged particles. And when these charged particles are moving, they create electric fields, and moving electric fields create magnetic fields. So everything in the universe gives off electromagnetic waves. Now, does everything give off the same kind of wave? Well, what I want to do is look at what we want to see here is every possible electromagnetic wave, is represented by what we call the electromagnetic spectrum. And we can break up all the types of electromagnetic waves into these 6 categories. These 6 categories, I listed them here. They're the radio, the infrared, the visible, the ultraviolet, the X-ray, and the gamma ray. These are the 6 categories of every possible electromagnetic wave we can have. What do I mean by every possible wave? I mean that they come in all different wavelengths, from the longest wavelength to the shortest wavelengths. The longest wavelengths are in the radio region of the spectrum. They're radio waves. These are the waves received by your radio in your house, in your car, whatever, and these are converted to sound and you hear the radio. That's how the radio waves travel. They're electromagnetic waves. They travel at the speed of light, and they have their lowest, the longest wavelength of all. The next category, as waves get a little shorter in wavelength, we call the infrared waves. The infrared waves are heat waves. Heat waves are infrared. The lamp, the infrared lamp at Burger King that warms up all the French fries, that's an infrared lamp. That's causing heat. That's warming up the French fries. That emits electromagnetic radiation. And that's heating the French fries. That's infrared radiation. That's electromagnetic. Then if I look at the category of waves that are even a little shorter than infrared waves, we get to this next category we call the visible. And when we get to the visible category, this is the only category of waves, the only wavelengths that our eyes are sensitive to. We can see visible waves. They come in different colors, right? We told them the colors of the electromagnetic spectrum, the red, the colors of the rainbow, red, orange, yellow, green, blue, violet. Roy G. Biv, something that's the way we sometimes remember them. Red, orange, yellow, green, blue, violet. These are the colors our eyes are sensitive to. So our eyes are sensitive to only, you can see here, there are 6 categories of electromagnetic waves. It's only sensitive to that category whose wavelengths are just right in the middle of the electromagnetic spectrum. And as we go a little further up, as the wavelengths become a little shorter, we can see the red has the longest of all the wavelengths because it's on the left side of the curve. These represent long wavelengths here. Long wavelengths or low frequency. On this side are the shortest wavelengths or the highest frequency. So as we move from here to here, you can see wavelength goes from short to long. Frequency goes from low to high. So the next category of waves is ultraviolet. Ultraviolet meaning right above the violet. Ultraviolet means above the violet. Infrared, remember we told you, look, is just below the red. So ultraviolet rays are now, as we get to shorter and shorter wavelengths, as we move to the right in this, we're going to shorter and shorter wavelengths. Ultraviolet rays carry a little more energy. Okay, they're shorter wavelength than visible, and they can actually do some damage. We know that in ultraviolet rays give us a suntan. Okay, these rays can actually burn your skin. And this is a trend you can see here that as the wavelength gets shorter and shorter and shorter, the energy in the wave gets greater and greater. Right here, in the ultraviolet region of the spectrum, as I told you before, ultraviolet rays can burn our skin, and that's how we get a sunburn. If we talk about the next category of waves, the next lower, the next shortest wavelength is the X-rays. And we know X-rays from the doctor's office. X-rays are so powerful, they can travel through our body, and that's how doctors take pictures of our bones. They can look at the bones because these rays are so powerful now, they travel through your body. Those are called the X-rays. And then finally, the most powerful of all the electromagnetic waves, the most energetic of all, are what we call gamma rays. And gamma rays are usually produced only in outer space, in violent explosions of large stars or something. They produce gamma rays, very, very dangerous waves. So you can see here, this is the electromagnetic spectrum, going from the radio, the longest of all the waves, the least energy ones, to the infrared, into the visible, and our eyes are only sensitive to this region right here. Then above that is the ultraviolet, the X-ray, and gamma rays. So these are the 6 categories. I've summarized them here on the right. Those are the 6 categories of waves in terms of electromagnetic waves of higher and higher energy. And as we go from the top of the chart to the bottom, the waves become more energetic because the wavelengths become a lot shorter. Short wavelength means high energy. Okay? It's short wavelength and also, as we see here, short wavelength and high frequency because you get more wiggles per second. You get higher frequency. So there's an example here. I show you here the flashlight, white light going through a prism. When light travels through glass, I told you as it slows down, it gets refracted. Each wavelength gets bent a different amount, okay, because each color represents a different wavelength. The red gets bent the least. The violet, or the blues and the violets, get bent the most. Their wavelengths are shorter, they bend more than the red ones. And because all the different colors have different wavelengths, they bend different amounts, and we spread it out into the spectrum here. And one of the first people to see this electromagnetic spectrum and explain it was Sir Isaac Newton. Sir Isaac Newton had a dark room with a shade in it and a little hole in the shade, and from sunlight coming in, and he passed that sunlight through a prism and showed that light was made up of all these little different colors. In fact, if you mix red, orange, yellow, green, blue, violet, you mix them in all the same amounts, you'll get white. White light is made up of all these different colors, okay? And if you mix all those colors together, you will get white. If you had red paint, orange paint, yellow paint, green, blue, and violet paint, mix them all together in the same amounts, you will get white paint. So white is actually not a pure color. It's actually it's a color made up of many different wavelengths, and our eyes are sensitive to those wavelengths, only these wavelengths in the visible part of the spectrum. We can't see radio, we can't see infrared, we can't see ultraviolet, we can't see X-ray, we can't see gamma rays. We can feel them, okay? But we know these rays, for example, X-rays, we know are very dangerous, right? When you go to the dentist's office and they go to give you an X-ray, what happens is they put a lead sheet over you. They put this jacket over you so that the X-rays don't travel into your body, because prolonged exposure to X-rays can damage your DNA. Okay, and you have to be very careful okay, of x-rays. Usually the x-rays in a dentist's office and a doctor's office are usually a little low power. They're not as dangerous as a higher x-rays, right? The x-rays on this part of the spectrum rather than on this part. Okay, but x-rays are damaging rays. Okay, and that's why you wear that jacket so that they don't go through your body and ruin and can do damage to you under prolonged exposure.